Throughout this lecture series, we've looked at a lot of different organometallic compounds. We've looked at their structure, we've drawn isomers, we did NMR studies, even dynamic NMR, but we haven't really looked at the formation of them and the driving forces behind ligand substitution, for example. And so that's the area of reaction mechanism, and of course it's tightly connected to the kinetics aspect of it, which are the rate of reactions. You know, some ligands go faster than others, and why is that? So that's kind of the focus of this little lecture here. It kind of is a hodgepodge of things. It has this and that in it, but it's all connected to kinetics and mechanisms. And so if you wanted to read up on it in that Shriver-Atkins book, it's mainly chapter 21, but I do dip into this and that. So let's take an example of a ligand substitution here. We are going to replace monodentate amine ligands with chelating ethylene diamine ligands across a cobalt-3 complex here. So both of those ligands are nitrogen 2-electron donors. They have about the same sterics. If anything, the ethylene diamine would be more difficult to latch on, but it turns out that it is the chelating ligand that will always substitute monodentate ligands. We call that the chelate effect, and that's mainly an entropy effect, right? And so if you go back and just simply look at the number of particles, we determine that there are 2 on the reactant side and 3 on the product side. So that's clearly an entropy effect. 2 going to 3 is an increase in particles, therefore an increase in entropy. Now, this is the first step here shown. So the K1 up there is an equilibrium constant. So these are actually at equilibrium, and I should show the arrows correctly. So we can, by increasing the Le Chatelier's principle, right, doesn't go away. If you increase the concentration of ethylene diamine, you are going to shift this equilibrium to the right. But regardless of that principle, all you need to understand is that all of these K's are larger than 1, which means the product sides are favored for all 3. However, K1 is always larger than K2, which is larger than K3. So we just have a little bit less of the triply substituted chelating ligand, so, or complex, with all 6 sides of the octahedral occupying a chelating ligand. So if we look at a chart of the magnitude of these equilibrium constants with respect to each other for different transition metal centers, starting from D5 manganese 2+ all the way to D10, which would make this oddball here that does this goofy stuff a D9 copper 2 complex. So these are the 3D transition metals, and these Ks are all for the hexaamine. Obviously it's not ammonia, it's amine, as I taught you. Hexaamine complex being substituted with a chelating ligand. And so the trend here is true for all of the transition metals, including the D9, but there's a huge discrepancy between the second and the third. So there's something going on that prevents the third one from going further to the right. So we have a little bit of dye substituted, and more so than we would expect. So let's see what's going on. What's preventing that third ligand from going on, from latching on and replacing the monodentate ligands? So for that, we have to go back and look at the ligand field splitting diagram of an octahedron. And so we're going to do this specifically for a D9 system. So this is a crystal field splitting diagram, but it's the same. If you remember, the difference is that the EG and the T2G would be non-bonding, so it wouldn't go down in energy. But what matters here is that both the x squared minus y squared and the dz squared orbitals are considered to be degenerate in an octahedron field. But if you consider that those 2 orbitals are quite different from each other, right? So the dz squared is this here, and this is the x squared minus y squared. And so could there actually be a difference in geometry, you know, that they're both octahedron, but in perturbation, meaning in the distance that the ligands go in and out. And so if we're looking at a system that has a single electron in the x squared minus y squared, so the 2 electrons here would be in the dz squared, we have fewer electrons in the x and the y axis, so that actually causes an elongation of the z-axis. So you see stretching. So that distorts, and we call that the Jahn-Teller distortion, the octahedral field by elongation of the z-axis, which makes it more difficult for that third chelating ligand to latch on. And the same is true for compression. So there's also a scenario where we have and so I circled the wrong one here. It's of course the 2 electrons is the d2 and the z squared. And so here we have the 2 electrons in, so let's take a look at a clean page here. So what that would do, if we have 2 electrons in the x squared minus y squared, we would have the opposite happening here, right? So we would have a compression. So we would be able to go in, since there's more electron density in this region and less electron density in the z region, so we call that compression. And either way, that is also going to prevent that third ligand from latching on faster, and that explains that phenomenon that we observe here. So this is called, again, the Jahn-Teller distortion. And if we look at the octahedral field before it is distorted, here's what elongation and compression would look like, right? So if you have elongation, meaning the x squared minus y squared ligands go in deeper, you see an increase in energy of that, and so they both have, there's a different way this splits. And so of course the opposite is true for the compression. Now we have more of a ligand interaction in the z-axis, and the dz squared orbital will go up in energy. So these two essentially switch. And so we also see a difference between the non-bonding orbitals here. They also split, right? So if it's the YZ that has a stronger interaction, it will go up, and these are still degenerate, and then vice versa. So this is just an interesting phenomenon. And so just to kind of have some fun with it, if we elongate that even further, we end up with a square planar splitting diagram that we saw for the ligand field theory. Okay, so this is actually in theory observed for not just copper D9 or any kind of D9 complexes. You should be able to observe this for D1, D2, D4, not D3, and then low spin D5, high spin D6, yada yada yada. And again, we're leaving out D8, and so I'll let you think about why that might be yourself. But it boils down to analyzing your diagram the way we did it for the D9 system. We basically said, well, is there potentially a difference between the configuration, whether we have the dz squared with a single electron or the x squared minus y squared. So if you kind of analyze the orbitals and where those electrons would be and the perturbation that is potentially possible, you can figure out why these systems here should, in theory, have different fields or just some sort of distortion. All right, so but for this should be D9, oh, D8, yeah, D9 copper is really where it is observed the most. So let's look at equilibrium constants of not substitution reactions, but addition reactions. Right? So here, instead of starting with a 4-coordinate or 5-coordinate system, we have a single metal center, and so this should also be charged, but since this is generic, we are leaving the charge out, so it also should go one ligand at the time. And so if your maximum number here, for example, is 6, so then K6 would then be equal to, I'll write it above because I have more room, it would then be ML6, the concentration of ML6, divided by the concentration of ML5 times the concentration of L, right? It's just the concentration of the products times the concentration of the reactants. We can also look at an overall formation constant, but we don't call those Ks, we call them betas. And so all that is like beta 3 would be a trigonal planar complex, and so it would you can express it all together. You can essentially say, well, if we have ML3 would be your product, you have the concentration of the metal, and then 3 of the ligands, right? So L to the cubed, right? So which is this is just a mathematical relationship that's pretty straightforward. Here's some other interesting facts or mathematical relationships. So if we actually look at a specific reaction here, we have a tetrahedral cadmium complex here that we're forming, tetramine cadmium 2, and so here we have K1, K2, K3, and K4, and as expected we expect K1 to be larger than K2, etc., etc. And you can determine what beta is simply by multiplying K1 times K2 times K3 times K4. So if you know those, you multiply them, and of course all it is, it's 10 to the 2.6 times 10 to the 2.10. That's just, you just add this up, 2.65 plus 2.1 plus this will give you that 7.19. So the overall formation constant is just a mathematical relationship, not really a big deal. We also need to look at the thermodynamic factors here, right? So we have enthalpy and entropy. And so if we are looking at the formation constant of the hexadentate, in this case we have octahedral amine complex, and we have the chelating ligands. So we're not substituting, we are looking at the addition of 6 amine ligands to nickel versus the addition of 3 ethylene diamine ligands to the nickel center. And so we get the 2 different betas. You can see that beta 3 for the chelating ligand is much larger, and you can actually calculate beta here by doing beta 3 over beta 6, and then that would also be equal to which is 9.6. So you can just do 18.3 minus 8.6, so that gives you a K of 9.6. And as I said, we have in order for a reaction to be spontaneous, we can pick we can use this K and determine that here we have a negative delta G, so that's a spontaneous reaction. Of course, delta G has 2 components, delta H minus T delta S, and in this case it's mainly an entropy driven reaction as we've determined. So we get negative 55 kilojoules per mole for the entropy, but it's also thermodynamically favorable. So we have a negative enthalpy, so this reaction will be spontaneous at any temperature. So that goes back to basic Gen Chem stuff, right? So in general, chelating ligands are always going to substitute monodentate ligands. So that's just a rule of thumb, and it's called the chelate effect. It's mainly an entropy driven reaction. But you may also want to consider thermodynamic factors, and so if you have a large ring strain, that could sway that or prevent that chelating ligand from going on. So in general, 5-membered and 6-membered rings are the most stable ones thermodynamically. So they will also, like in the case of the ethylene diamine, we make a 5-membered ring here, and so you also need to consider that we have tetrahedral centers all the way around, and so it's not like benzene and phlad, so that this 5-membered ring is puckered up and down a little bit, just like cyclohexane would be with the chair and the boat. And so that actually it turns out that a 5-membered ring is more thermodynamically stable than a 6-membered ring. Okay, so anything larger and smaller then might add some ring strain, and so you may not be able to make a 3-membered ring like a carboxylate. It depends on other factors, not just entropy. But And speaking of stable and unstable and labile inert, those are terminologies that sometimes get confused. So stable and unstable refer to thermodynamic aspects of a reaction. So for example, if you have a diamond, it's going to be unstable, right? Because we do know that thermodynamically diamond will convert to graphite, except it's a very slow reaction, and that's a kinetic term, and so slower would then be referred to as inert. So you can have an unstable compound that is inert, meaning it will slowly convert to its thermodynamic product, which will have a large negative change in energy, right? Exothermic processes are thermodynamically favorable. And so this applies to ligand exchange reactions as well. And so we here have a generic substitution of L by L prime. So here you're just exchanging one of the ligands. And so it is possible that you can have something that is thermodynamically favorable, like the substitution of aqua ligands with, so if you have a solution of hexaamine cobalt 3 and you put it in the solution, an acidic solution, your delta H is going to be negative, so that means this product is thermodynamically favorable, right? So that makes this unstable, but it's also inert, right? So this complex is inert. It just reacts very, very slowly, right? So it does exchange, it does kick out amine ligands and take up, but it's just a very slow reaction. But if you look at this K here, right? So once this formed, there really is no going back. So this equilibrium lies very, very far to the right. So there's very little going back. I mean, look at this K, 10 to the 25. Here's an example of the opposite, right? We have a stable but labile complex. So tetracyano nickel 2 is stable. So that means the K is very large here. We have this the product formation, but it's also very labile. That meaning it does actually exchange ligands very, very quickly here, right? But it takes up a cyanoligand back up. So you actually can do some isotopic labeling here, right? So you can have carbon 14 labeled cyanide, introduce it, so you have a solution of this complex. Let's say it's nickel tetracyano nickel 2 chloride or something like that. So you have, if you introduce some isotopically labeled cyanide ligands, you will actually find that your product will incorporate some of the isotopically labeled, so which is proof that there's a ligand exchange that's very quickly, but overall the concentration of your nickel complex is large. Anyway, that's just vocabulary. You should know the difference. So in general, if the half-life of an inert complex is larger than 1 minute, so that means it's very slow, we call that inert. And if it's faster than a minute, it is going to be a labile complex. Now we're going to look into mechanisms. Okay, similar to organic chemistry, where we have SN1 and SN2 reactions, first order and second order reactions, we have a similar type mechanism. So if we have a complex that dissociates first, so we call that a dissociative mechanism, right? So we're talking about ligand exchange. So we're going to kick out X, and the two types are associative and dissociative, right? So if we have a complex, and a dissociative mechanism means the ligand is removed and the new ligand comes in. An associative mechanism would mean that the ligand attaches first, the incoming ligand, L prime, or in this case we call it L, or Y, sorry. So Y comes in and attaches, and then your ligand leaves, the X leaves, and usually what happens, this type of mechanism, dissociative mechanism, is more common for large coordination numbers, right? If you have coordination number 5, 6, or 7, it's less likely for the incoming ligand to attach first. It's more likely for an attached ligand of the complex to dissociate first, and then so those are the labile complexes that would be more likely for this mechanism. Anyway, so that means that the rate determining step depends on how fast X leaves, and so once X leaves, Y can come in and attach. So the fast reaction. So we have a first order rate law, which the concentration only of the ligand, the coordination complex matters, and not the concentration of Y, right? So that's irrelevant. So it's first order kinetics for a dissociative mechanism. You can kind of draw this here. The reaction coordinate, it depends, as I said here. So the transition state will have both the incoming and the leaving ligand disconnected completely. That is a pure dissociative mechanism. And then once it's detached, Y can come in quickly and form the product. So we call that a dissociative mechanism. The associative mechanism means we have the incoming ligand Y first attaching, so now the concentration of both the metal complex as well as the ligand matters, and so we end up with a second order rate law here, right? Concentration of ML5X and concentration of the ligand. So that's the slow reaction. Again, we have this is more common for 4-coordinate and 3-coordinate complexes, or smaller ligands, where the ligand can come in and attach to the center first, and then a leaving ligand will go. So here the transition state has connections to the leaving ligand as well as the incoming ligand. So that's the big difference if they are pure associative or dissociative mechanism. You should be able to draw the mechanism, you should be able to know what the transition state is, and maybe you can even draw a little mechanism out for me if I ask you to do that. We'll do this in a second. The reality is a lot of times we have some mechanisms that are in between. We call them inter-exchange mechanisms here, right? So it's kind of a in-between type thing. And so what we do is for the transition state, we draw a dashed line between the incoming and the leaving ligand. So that's the difference. Those are the three that you need to know: dissociative, associative, and inter-exchange mechanism. And so here, for example, is a mechanism that is dissociative here, right? No, I'm sorry, it's associative, right? So if we have a 4-coordinate system here, the ligand can either come in from here or from here. So it's associative first, it's making the connection, and in this case here, we now have the two ligands that are labeled C1 and C2. They are cis in the square planar complex originally. And so, by the way, this is going to become important for palladium and platinum square planar D8 systems. And it will lead to retention of configuration. And so here's why. So once you have associated your incoming ligand, the leaving ligand X, and here we have T, the ligand trans to X, they rearrange to form a trigonal bipyramid. So if you were to draw a mechanism out like this, what you want to do is you also want to indicate your geometries, like this is square planar, this is a square pyramid, and then this is trigonal bipyramidal, and then once your ligand X leaves, it can now rearrange to form a square pyramid and then kick out X, and so we have the new incoming ligand that is trans, or exactly in the same position. So we still have the cis ligands that were cis first, whereas if you had a dissociative mechanism, you would have the opposite, right? So I do have a little bit of room here. So if X kicked out first, we would have this scenario here, and then this could actually go into a trigonal planar configuration. And so once you have a trigonal planar configuration and your incoming ligand comes in on top or bottom, you're going to get scrambling. So this is kind of the proof that for platinum and platinum is PD. Palladium is PD, for crying out loud. Anyway, all right. So what we do with that in this mechanism is we get something called the trans effect, right? So this only is for D8 square planar complexes. And so there is actually a activity series, and it's the exact same thing that caused the splitting diagram to be, you know, the ligand field splitting diagram, the delta naught to be large. The stronger back bonding type ligands like the pi acceptors, like the carbonyls and the cyanides, they're the strongest trans directors, and then the pi donors and the sigma donors in the middle. So you have access to the series. All that means is if you are doing a substitution here of this platinum compound, if ammonia comes in, so it doesn't matter where this ligand is. What you need to find is the strongest trans director. So it's either the amine or the chloro. So go find that. So the chloro is here, and the amine is here. This means that the chloro is the stronger trans director. So what we have is the amine is only going to go and substitute trans of the chloroligands, right? So it's either going to substitute here or here, but never here, because the amine is weaker than the chloroligand, and so again, it also has nothing to do with that this is the chloroligand and stronger. It has something to do with the ligands that are staying on. So this and this is going to eliminate one of those chloros. So in this reaction, what we find is only the cis product here is formed, and we have 0% of the chloro, where the amine would actually substitute trans to the other amine. So that does not happen. So how do we deal with that? Well, it's not that complicated. All you have to do is, again, we're going to draw this out. We have platinum, 1, 2, 3, and so NH3, 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 and so we have the chloro here. It's important that we pay attention to the charge. And so the strongest trans director, as we know, is the chloro. So the only substitution we're going to see is right here. So the only product formed here is this PT and Cl, Cl, and then of course this no longer has a charge because we are substituting a neutral amine ligand with a chloroligand, so this is now neutral. So this is the only product we expect here. So again, all you need to do is look at the ligands that are attached, find them in your chart, and whatever is coming in, it doesn't matter whether this is hydride or water, the strength of the incoming ligand doesn't matter, only what's attached already. And so the ligands that are going to be substituted are trans to the strongest director. Again, in this case, it's going to be trans to this chloro, so this is the only one that gets replaced. Let's practice a couple of those. So if we, instead of chloro, use iodide, we now have the iodide that is stronger than the chloro, and so it doesn't matter, as I said, and so you're still going to end up with a complex that has the iodine trans to the chloro. So this is the product, but you also are going to replace the amine, so you have a second product in this case where we have iodine here, and always just use one, just use one. And so what happens to the charge here, this still has a negative charge, but this now has a -2 charge. So this has 2 products, and then so here we have platinum and then 3 chloros and the iodine, and so the iodine is going to be the strongest trans director, so we're only going to be replacing, so this has a 2- charge, we are only going to be replacing the chloroligand. So our product here, so it doesn't matter what this is, it just matters that the iodine is stronger than the chloro. And so we have PT and then and this time it's a methyl group that gets attached, so this also has a negative charge. And I apologize for how sloppy it is. I'm trying to fly through this stuff, which is boring me to death. And you know what? You can practice this on your own, have some fun with it. It's definitely going to be on the exam. The last thing that I want to show you is a mechanism, an electron transfer mechanism here. The person who studied this, Henry Taube, a Canadian chemist, won the Nobel Prize for his electron transfer reaction. So there's two different ways that electrons can transfer. You know, those are redox reactions. If you take a look at this reaction here, what is interesting is that we don't have ligand exchange here. We have the same coordination sphere. And so also if you assign oxidation numbers, each of the metals here, so obviously the electrons are transferred from the metal, right? So we have cyanide, which is -1, so that makes this +2. And then over here we have +3. So this is your oxidation here, which means the electrons are transferred from the iron to the iridium. And so here iridium is 4. And over here iridium is 3. So that's the reduction. All right, so that's your reduction. And so the electrons are somehow transferred through the spheres. Okay, and so the way to look at that is they call that an outer sphere electron transfer, where you just have electron transferred without leaving off the ligands. Now, if you have an inner sphere electron transfer, you will see, so this is how you can distinguish the differences if you are given a reaction. Noticing that nothing changes here except the oxidation state of your transition metals. That means it's an outer sphere electron transfer where electrons basically jump from one complex to another. If you see ligand exchange, like here, the chlorine is transferred to the chromium, and so your product will take up a water molecule here, so that means it's an inner sphere electron transfer, which are much slower. So this is kind of it for this chapter. So see you for inorganic part 40-45.